and then we will start after 2 minutes like that.
Sure.
So now we are live and we are recording. So we will just wait for 2 minutes because participants will join up. I think we have attendees now. We have 4. Still counting. In about a minute, we will start the presentation.
Okay, so are we on air?
Yes, Doctor. We are live and we are recording.
Okay, perfect. Thank you so much for the introduction, Robert, and thank you everyone for the attendance. We're going to be talking today about nanotechnology. It's a very interesting topic that addresses the advances in many fields nowadays. Now, if we're going to be moving further and start talking about what is a nanotechnology. Well, a nanotechnology, it's these kind of collection of technologies that are based on materials that are within the nanometer dimension. How is that important? Well, before getting into that, we need to give you an idea of what a nanoscale is. For example, if we have just a schematic representation here, if you have 10 hydrogen atoms that are laid side by side, it will be in the order of about 7 nanometers. Imagine that, 10 atoms that are side to side, you get into a 7 nanometers. So in this presentation, we're going to be talking about devices and systems that are within that scale. For example, if you're going to be having a DNA is about 2.5 nanometer. So biologically speaking, the DNA dimension is about 2.5 nanometers. If you are talking about a human hair, it's about 50,000 to 100,000 nanometers. If you are talking about a red blood cell, it's 7,000 nanometers. So this gives you a clue about how micro or how nano, how small is this kind of fields. And we indeed having too many aspects. If you're going to be addressing a nanotechnology, it's going to be biased in the medical direction. It's going to be biased in the electrical direction. It can be biased in the mechanical directions. It can be multidisciplinary. So indeed, we cannot handle the nanotechnology all together in one presentation. In this presentation, the nanotechnology will be mostly in the flavor of electrical engineering. This is one of the most important fields of the nanotechnology: the electrical, the electronic, the optical, the the nanophotonic, and the nanosystems, the nano computers, the nano networks. All of these things are based on the fact that we can devise a system, we can devise a component that has a dimension within few nanometers. We are even we get into details through this presentation. We are even having materials that are with an atomic thickness. For example, graphene, or two-dimensional material that we will talk about it today. It's being increasingly used in devising, electronic and optoelectronic and laser-based systems. These materials have a thickness of only 0.3 nanometer. So you see how delicate is this kind of technology. But the importance here is that these kind of materials that are based into nano-dimensional devices, nano-dimensional synthesis, I should say, the material itself is being with such a small dimension, they show a very significant functionalities that are unprecedented. It wasn't possible before getting into such a thing. So as we said, if even you are talking about a red blood cell, it's thousands of nanometers. So we are talking about these devices and these components that could be small in comparison to a blood cell. Nowadays in biomedical engineering, for example, people talks about lab on a chip. So you're going to be talking about an entire lab that can be implemented inside a chip. Of course, that cannot be done without the help of such technology, which is indeed, I would say it's about 40 years old, but it's being implemented more and more lately in the maybe last decade. Okay, so having that said, we're going to be moving at the beginning to the history of nanotechnology. Indeed, the earliest, let's say, prediction for nanotechnology was done by Professor Richard Feynman. He's a physicist, he's a Nobel laureate, and he was the first one. People called him the father of nanotechnology. He was the first one who predicted that if materials are implemented in a subatomic range, in a nano range, the material can show functionalities that cannot be based into a natural material. We will see into different examples throughout this presentation. If you're going to be relying into natural material, just like gold, just like silver, just like silicon, just like aluminium, there will be several limitations in achieving functionalities. However, if you start to design what's so-called nanoparticles or nano layers or two-dimensional materials, which is just a material that has a thickness, for example, two-dimensional material, just a material that has a thickness of nanometers or sub-nanometers, new properties, new behavior will be not just new one, it's a behavior that can be engineered, will be appeared. Engineered behavior that throughout, a well-designed, a proper design of the materials one can achieve is a resulting fruit of the nanotechnology. Just to complete the history aspects, in 1947, after Richard Feynman, there was a Japanese scientist who created objects and features in the nanometer scale. The journey continued after that, by a number of engineers and a number of scientists, those who were able, and nowadays it's a reality, those who were able to implement devices based into a nanotechnology. Now it's a reality. Now we are having devices commercially available. We use it in energy sector. We use it in environmental sectors. We will have different examples today. We use it in wireless communication sector. We use it in low power systems. So if you want to design a system or a chip or a microprocessor that consumes the least amount of energy, it has to be based into nanotechnology. So why does it matter? Why nanotechnology? It's been so well said that the microtechnology and microelectronics were the revolution of the last century. In having these computers that we are communicating right now is based on the microtechnology. And now the nanotechnology will be the revolution. It's predicted to be the revolution of the coming era. So we are expecting to have computers that are in the nano size. We are expecting to have sensors. We are expecting to have networks. We are expecting to have medicine assisted nanotechnology. So this kind of technology is entering, and it will take over more and more in different sectors, including information technology, including medicine, including energy, including environment, and more. So in understanding the nanotechnology and having these devices that are based into the nanotechnology, enabling many applications is so much vital for the development of our daily life. I said it several times since the beginning of this class, since the beginning of this talk, having the devices in the nano size, having the material in the nano size, it makes differences. It brings new impacts, new effects, new functionalities. It gives new behavior and so on and so forth. Why is that? Well, I do like to get deep into that, but this is because of the quantum effect. Quantum effect, it means that once you start to confine the physical material into a dimension that is comparable to the atomic dimensions, which is nanos and subnanos, the behavior of the electrons, which is the basis for the materials behavior, starts to obey a different approach. And this approach, in short words, it's the quantum effects starts to appear. So without getting into what a quantum effect and how electrons starts to behave like a wave rather than a particle, and how you start to see quantum effects that do not appear in the classical life, in the larger scale life, we can present it differently. We say that materials with reduced dimensions down to the nanoscale show very unique properties based on the quantum effects that we don't like to get deep into it. For example, this is the best thing that can one demonstrate the impact or the effect of shrinking the dimensions down. For example, opaque substances become transparent. Copper, for example, at the nanoscale becomes transparent. Stable materials turns into unstable and turns into the possibility of engineering the evolution of that material. For example, solid materials turns into liquid like gold, even at room temperature. So there are more, of course, and we can talk more about things, but the point here is the material, which is the basis of the, when you design a device, it's nothing but a collection of material, different materials layered in a certain way, connected in a certain way. These kind of materials will show a unique and significant evolution, a significant behavior, significantly different behavior once you get into once you get into a nanoscale dimensions that will enhance the quantum behavior of the electrons that involved within these kind of materials. So the property of things also change when they are getting smaller. Quantum effects, as we said, is the basis or the logic that can explain the material's behavior at that level. So as an electrical engineer, one of the first things that come into your mind is graphene. Graphene, people call it, the super material. They call it the miracle material. It's nothing but, it's a graphite. It's nothing but a lattice of carbon that has a thickness of 0.3 nanometer. So having that material with an atomic thickness brings it into too many different applications that wasn't possible before. First of all, if you're going to be looking, this material, graphene material, has a very unique optical, mechanical, thermal, properties. So, for example, it's 200 times stronger than steel. If you bring a steel with the same thickness, this material, graphene, is 200 times stronger than the steel, and the same time, it's 1,000 times lighter than paper. Maybe it's not mentioned here. The conductivity of this material is huge. The conductivity, electrical speaking, the electrical conductivity of this material is controllable. Engineer can make or turn the graphene into a very conductive or less conductive by applying a voltage or by applying or by radiating an electromagnetic wave. So this is indeed, I would say, the material of the century. It will be, and it has been used commercially. It has been used as super material that will intensify the application of many devices that we'll talk about it here. And scientists are predicting more application of graphene in different sectors, including biomedical sectors, electronic sectors, and more. So graphene, as we said, is one atomic thickness layer of carbon atom. Now, it is the thinnest material that we know. It's about 0.3 nanometer. Despite that, it's very stable. It can be landed alone. It is very strong, much stronger than steel, and at the same time, it's very light. So graphene was recently discovered, or was recently synthesized, I should say. So one of the very, at the beginning, there was a patent reporting, synthesizing graphene in 2002. Then in 2004, two scientists from University of Manchester were able to isolate a single graphene layer. They got a Nobel Prize after that. And after that, in 2010, they got a Nobel Prize for their work. And then since 2010 till the current time, which is a relatively very short time, it's only 11 years, graphene has entered in plenty of, of applications in different themes, in different disciplines. Abu Dhabi University, we have a group at Abu Dhabi University that's active in graphene from the optoelectronic perspective. So if you're going to be looking into the electrical properties of graphene, you will find it with a very large electrical conductivity. You will find it with a low resistivity. Of course, if you have it as a large conductivity, the resistivity is small. Also, it is chemically stable. It can be turned into a superconductor if you just cool the graphene to very small temperatures. Resistance will disappear and starts to behave like a superconductor that can be used for quantum devices, and quantum computing, the new, era that it's coming. Graphene has a vast of productivity in different applications: chemical, mechanical, civil, electrical, medicine, you name it. And it always proved to be pretty much a unique material serving into these kind of themes. What they want to say here, it is the world's first two-dimensional material. We know that. There are more time. What do you mean by two-dimensional material? It's a material that has a thickness which is pretty much close to the atomic thickness. So zero thickness if you wish. It's 0.3 nanometers, it's not a zero, but classically it's zero. Now, nanotechnology, which is graphene, is one application of such a nanotechnology, one result of such a nanotechnology. It's very important in many themes, in many different applications, including electronics, nano satellites, NIMS, which is a nano electromechanical system, in energy, biomedicine, and environment. So we will briefly come through all of these we will come across all of these kind of different themes and briefly mention how nanotechnology is indeed bringing a lot of new application, a lot of superior performance to each and every theme. Now, electronics, for example, carbon nanotubes, which is nothing but graphene that is in a form of a tube, are taking over. It's replacing silicon as a material for making more efficient microchips, and graphene make it an ideal candidate, for example, to develop flexible touchscreen. Flexible touchscreen is one of emergent technology that is coming. It will come more and more. It will make a very efficient systems. These kind of touchable, what they call flexible touch screen, they can be used in biomedical applications. They can be used for, it's very light, it's very efficient, it's very convenient. So it can be used in aerospace, it can be used in entertainment, whatever you name it. It's a revolution that's coming to the electronic sector. So here they're saying that using nanotechnology, chips are becoming faster, more efficient. They are becoming smaller in size, more compact, and they are becoming as well with less energy consumption, which, for example, is very, this kind of, using the batteries for a longer time. We are having nowadays batteries that are for long life, for 40 years, for 60 years. Thanks to the proper design of these kind of charging system, and thanks to the low power, consuming system that's attached to that battery. It's very convenient in many cases. It's for the aerospace application where you don't have the opportunity to look after the charging system and replacing this kind of batteries. It's important for sensing systems where you need to land your sensor in a harsh environment and so on. Also, optical nanotechnology is a very important, let's say, development of the nanotechnology. In optical nanotechnology, devices, computers, and networks are based on light to transform information rather than the electrical signal. We know, people that are specialized in laser systems, they know that confining light into a small cross-sectional area is very challenging. So, for example, if you're going to be talking about an optical fiber, optical fibers can be made up to few micrometers, but if you try to minimize the optical fiber cross-sectional area, you lose confining the light. The light will diffract and leave the structure. However, nanotechnology was able, thanks to the graphene, thanks to the plasmonic nanotechnology, was able to squeeze light even to a nano cross-sectional dimensions, meaning to say that we can make the light and the signal that is laser, which converting light, confined and controlled within a nano dimension. This will help coupling between optical systems and nano electronic systems, and one can, at the end of the day, come up with a nano components, or with the nano systems that are partially, part of it is electrical, part of it is optical, and so on and so forth. And optical signals have a benefit of low loss. It has a low loss. It can be transmitted over longitudinal distances, and so we together, thanks to this kind of technology, we can squeeze laser, we can squeeze light into nano waveguiding dimensions, and we can connect chips to each other using light at the nano level. So a flexible display screen, we have already said that, and this was not possible without the nanotechnology. Nanotechnology using graphene and using other kind of molecular in designing and synthesizing moleculars at the nanoscale, where the secret behind having a flexible display screen. Now, nanochips and nanocomputers, we already said that, but it's good to emphasize it again. Thanks to the possibility of having this kind of unprecedented properties of nanomaterials, we can design nanochips and we can design nanocomputers. Nanocomputers could be as small as a piece of salt that can process information at a speed that's higher than the today's computers. Imagine how powerful is that tool. And once humanity were able to devise systems with dimensions at least than a piece of beam, that would be it is there, but optimization is indeed being tested, and devices are being tested and being optimized, and there are more to go. But in principle, things are being there, and we know that nanochips and nanocomputers they are already there, but they are taking more and more portion of the market nowadays. And in future, we will have a very efficient nanochips and nanocomputers. So nanocomputers nowadays, if you are going to be talking about nanocomputers that are based in quantum technology, size-wise they are very big, and the reason of that is we need to cool down the material to 0 Kelvin, so that we can experience so that we can experience quantum effects, and we use it for quantum processing. But however, the core is very small, and we hope that these kind of obstacles can be solved. The application of quantum nanocomputers, including many benefits of solving very sophisticated problems that would take thousands of years, hundreds of years to be precise, by classical computers to solve. Now, advantages of nanochips, they are, of course, given the dimension is very small, so they are super fast. They're reducing the materials, and thus they're going to be cheaper. They are consuming less power, so efficient, compact, and super fast devices can be achieved having that said. Now, name by name, we're going to be mentioning the nano satellites. Nano satellites, it's not in the nano size. It's like centimeters almost. But if you compare nano satellite with the actual satellite, you will find it like super small with respect to the typical satellite. Let's say all of them are actual satellites. But if you compare the nano satellite, which is about 10 centimeters by 10 centimeters to the power 3, so you'll find it pretty small. These kind of satellites are completely functional. They have their own powering system. They have their own communication part. They have their own mechanical stabilization, and so on and so forth. And they perform as a satellite. They are cheap to produce. They are cheap to launch, and they perform very strategic functionality at many points. So it's not based into the nanotechnology, but it uses nanotechnology at some point when implementing some devices inside it. But the name of Nano Satellite comes after the fact that if you do, if you compare the size of this satellite, which is in centimeters, to the typical satellite, you will find it's like a nano meter with respect to a meter, the same ratio. So nano satellites, they have onboard computers, they are electrically powered, they have communication systems, they have control and subsystems for communication, and so on and so forth. So they are small in size, they are lower in price, and the development of such a satellite won't take a long time, maybe 8 months, for example. Now, NIMS is an actual systems that are based on nanotechnology. It's a nano electromechanical systems. These kind of systems, they could be sensors, they could be actuators, they could be transmitters, receivers, that half of it or part of it is optical or electrical and part of it is mechanical. Based into the nanotechnology, the dimension is in the nano size, and they do pretty much very functional applications, including body-centric devices. For example, we have body-centric devices that can be implemented inside the human body, and we can communicate with these body-centric devices using such a nano or NIMS, a nano electromechanical system. So they are very efficient, they are very compact, and they have a very low consumption of power. If you look into this is an examples of NIMS or nano electromechanical systems. Typical devices that are based into NIMS technology, like the accelerometer that you have in your mobile phone, small robots or minimized robots, medicine and body-centric materials. Also, we use it in biotechnology. Pretty much, it won't be possible without the nanotechnology and without the nanomaterials that would enable having a microprocessor with that small that can be landed or implemented inside your body. Now, nanotechnology in wireless communication systems is absolutely there. We use it to have an efficient transmitters and receivers. We have a nano antennas as well. And when you say a wireless communication system, it means information or mobile systems, but also this kind of wireless systems could be for example, monitoring your health. It could be a body-centric wireless communication system that is communicating with the station, reporting your kind of vital signals of your body. Now, nanotechnology in wireless communication systems enables many applications. So it improves the radio frequency components, the radiation. It increases the usage of RF frequency. It uses low power. It implements low power systems and so on and so forth. Here, I am sharing with you one of our applications at Abu Dhabi University, where we are using a graphene, which is a nano-based material, to have a new functionality of entangling microwave and optical signal. Entangling them is like you get them connected to each other despite distances, despite separating distances. And this won't be possible without implementing a graphene in this proposal. So also you can have a nano network. The most fundamental elements to materialize nanotechnology is the development of battery-free nano devices. It's thanks to the fact that the device is nano-wise, so we can have it pretty much consuming the least amount of energy, and thus either you're going to be having a long life battery, or it could be without battery. It could be relying on harvesting energy from the environment. So you can, thanks to these kind of technology, you can get a nano network that it could be long life one without consuming any energy. It could be expanded over different tasks with different applications. Could be biomedical applications, nano communication, for example. You can communicate between devices while you're having different kind of radio frequency spectrum in between, different kind of information. And so it could be also for sensing. You could send it to the outer space and leave it there, and since it consumes the least amount of energy, it keeps signaling you for a very longer time without maintenance. Now, nanotechnology also is very important in energy. All of us know the importance of renewable energy, but the efficiency of renewable energy, if you talk about solar cells, reach a specific limitation, limited by the efficiency of the material. The material's efficiency can be boosted by engineering this material using the nanotechnology. So, for example, here, you can have a much more efficient, maybe next slide, you can have a much more efficient and much more reduced cost solar cells using nano-based material. It will be more efficient, it will produce more amount of electricity using the same amount of radiation, the same, being subjected to the same amount of sun radiation. It could be flexible, so it can be, properly maintained everywhere. You could maintain it. It's not necessarily you have a field for that. It could be, indeed, sometimes they just, it's similar to a paint. It's just, you can have it covering your home, covering your car, your vehicle, and so on and so forth. So you have a multifunctional solar cell. It's extremely high efficient, occupation of a very thin area. It's generation of a very high power, and you might have more than one layer, thanks to the nanotechnology that enables materials that are capable of doing such functionalities. Here they are talking exactly about the same topic, which is the flexible solar cell. Flexible solar cell, the same thing, they are based on nanotechnology material. They are efficient, they are light, and they can be used in many different positions. Top of your car, it's just like a film that you can attach it to anywhere, available area that is properly subjected to sunlight. Biomedicine is another field that uses nanotechnology. Now here you can look at it into different aspects. It could be the biomedical device you designed or implemented using nanotechnology. It could be the delivery of the medicine. It could be the devices that's used for testing. It could be the imaging system. All of these are indeed have a very good overlapping with nanotechnology. So here they say nanomedicine refers to the area of science that combines nanotechnology with drugs delivery and diagnostics as well. So it could, be, as we said, it could be used for example, let me just say it off the record here. It could be used, for example, for cancer curing. When all of us, this is not my expertise, but all of us know that radiation can be used for the medication for cancer. And the principle of radiation is just you heat that kind of piece, you heat kind of this defected area by subjected to the radiation. Now the problem is sometimes the heat is taking over even good functional parts of your body. Having a nanotechnology, you can implement nanoparticles in the defected parts, and thus by radiating these kind of nanoparticles, which is metal nanoparticles, can be heated and only damaging the cancerous cells. This is a little example. You can also use it for better imaging and for better diagnostics, and we can use it also for body-centric systems. This, for example, is a proposal of our group where we have proposed implementing a transceiver inside the human body that is operated over or using terahertz, not radiation, optical radiation, not atomic radiation, it's terahertz radiation. And the purpose of that, this terahertz radiation is not harmful to the human body. It's only, it's not ionizing. It's only can communicate with the structure that is implemented inside to the end of monitoring and drug delivery. Here, for example, they are talking about the deliver medication directly to the cancerous cell to minimize the risk of damaging healthy tissue. Exactly the same thing that we have talked about. It can be used nanotechnology for and using nanoparticles as well for imaging purposes and besides the drug delivery. Environmental in the environmental remediation. Nanotechnology also takes a very important functionalities for the environment. It can be used for processing different aspects, of materials that interest us, water, air. It can be used for assessing the quality. It can be used for monitoring this kind of environment, very important. For example, here, this is a work that was again established by our group at Abu Dhabi University. We have designed a gas sensor that is very sensitive, to measure the different kind of gases, that's very sensitive to a very low concentration of gases, and the principle of that is that we're going to be having a radiation, like laser radiation or near infrared radiation, or it could be a broadband radiation, to a structure that we have designed. And the absorption of this radiation in this structure depends on the gas that's surrounding this kind of structure, very seriously depending on to that. This structure won't be able, without a proper design, in the nano size. Look, it's gold, silica gold, a ring gold material, and this won't be possible. The kind of behavioral, the detection, the sensitivity of the surrounding gas won't be possible without designing these dimensions within the nano size dimensions. This is a nanotechnology. Here, for example, this is another example of using optical fiber to assess the quality of water. This is another work that's published for us recently. And here we use this kind of technology to assess. It's an optical fiber that has small dimensions, it has small crystal dimensions inside, while it can test, if you just allow the water to go through a small hollow core, it can assess the quality in no time, without any chemical processing. It's instantaneous response to the quality of the liquid or the water that you are subjecting. Air filtration using nanotechnology is there as well. And it's a field by its own that people can use it to monitor the air quality. So in conclusion, nanotechnology is having too many aspects to develop to develop many different fields, including computing, including sensors, including medicine, including renewable energy, including environment, including biomedical energy, and more. It's a very interesting field. It has just started, and there are more to come. So thank you so much, and I open the floor now for any question. Robert?
Hey, Doctor.
Yeah,
so for the participants,
tell me, please.
Sure, Doctor. So for the participants, if you want to ask a question, you can raise your hands. I can allow you to talk, and you need to unmute yourselves.
So I'm writing down my email. Here's my email. You are more than welcome to come up with, any question, any discussion, anytime. You just need, and here's my website. You can download any paper, you can any piece of information. You are always welcome.
Hi, Mr. Tanzil.
Yeah, assalamu alaikum, doctor.
Alaikum salam.
My question is that, thank you for the great presentation. It was really nice. And my question was that there are also nano SIM cards. So what is the reason behind that?
Well, Tanzil, the one that's commercially available,
Yeah.
nowadays, they talk about nano SIM cards, is just a name. And, just like the name for Nano Satellites, they want to send the point that this is pretty much very small, but it's not using the nanotechnology. However, using nanotechnology for kind of security purposes is pretty much possible. You can, for example, you can synthesize structures that are encoded at nanoscale, and it will be very, very secure, and so it's possible. But the one that commercially, it's just a name.
Okay. So thank you for your presentation.
Thank you, Tanzil.
Thank you.
Thank you. Okay, gentlemen, ladies and gentlemen, you are more than welcome to email me anytime. We can even chat. We can talk about anything, any aspects that's related to nanotechnology. Nanotechnology is very, very diverse field. It's not just what I presented today. What I presented today mostly from the eyes of electrical engineer, optoelectronic engineer, and there are more to be said even in this sub area of nanotechnology. But if you talk to a mechanical engineer, or if you talk to a chemical engineer, or if you talk to a biologist or a biomedical engineer, they can tell many different stories as well. Okay, so maybe we need to conclude if things are all good and we have no questions.
Yes, Doctor, there are no questions, the question and answer, and also on the chat. But if you have a question, you can raise your hand. I can allow you to talk, and you can just unmute yourselves. But as of now, I don't see any question in the question and answer.
I would thank you very much. We have a very good number of participants. I appreciate your attendance, gentlemen and ladies, of course. I know that questions might arise later. They might come at a point. You might feel shy now to talk online. That's absolutely fine. Although you are encouraged. Here's my email. I'm available at any time, and let me know your opinion. Thank you so much.
Thanks, everyone. Thank you.